this section we will look at the base kets and transition amplitude. And we know that in Schrodinger picture, the state of the system changes like alpha. It goes state at alpha, which goes like u alpha, right? Where u is the time evolution operator. Time evolution operator. I mean, we know that it's. I mean, if the Hamiltonian is independent of time, and if t0 is 0, I mean, it's u is nothing but e raised to minus I by h cut h3, right? And now we would like to ask the following question: and what will happen to the base kets if under time evolution? Okay, that's the question we want to ask. So, but before that, I mean, what do I mean base kets? Base kets means, I mean, that suppose, any state you expand in terms of the eigen, so given an arbitrary state alpha, you always expand it in the, it's like summation over a prime, C a prime, A prime. And how do you, generally you take A prime as the A primes as eigen vectors of some observable A. So basically, these are the eigenvectors of an observable A, right? So so you know that if A acting on A prime, which is equal to A prime. This is the eigenstate. Now, suppose that you work with Schrodinger picture. In the Schrodinger picture, the vector A, A is AS, right? Sorry, the operator AS, which is fixed in time, right? AS, which is acting on A prime, which is equal to A prime. So you can see that so the eigenvector, at all the time the operator is the same. That's what the definition of in the Schrodinger picture, the operator is always independent of time. It's the same. At any time, right? So AS. So basically, these A primes are the eigenvectors of AS. AS doesn't change, so of course AS won't change. So you can say that in Schrodinger picture, the base kets in Schrodinger picture, the base kets are the same. They won't change. Are the same. So they won't change in time. Okay. Now let's ask, what about the base kets in the Heisenberg picture? Okay. In the Heisenberg picture, we know that the state of the system, is independent of time, but whereas the operator do change, right? So to begin with, so immediately you may think that, oh, since the state of the system changes, it doesn't change, the base vector won't change, but that's not the story. So let's try to see it. Okay, so in the Heisenberg picture, the operator, say A changes like A or AH. AH is nothing but which is equal to U dagger AS U, right? U dagger AS U. AS is fixed in time, and the time okay. So AH is a function of time, right? It's equal to U dagger AS U. Okay. Now let's consider a state. I'm just taking a state which is U dagger A prime. Okay, where A prime these A primes are the eigenvalues of AS. Okay, they are the eigenvectors of AS. And now let's try to operate this AH. I'll try to operate AH. AH is basically U dagger AS U on this. So what do we get? U dagger will be identity. Then AS acting on A prime, which will give you A prime. A prime into U dagger A prime. That means now if you look at this is nothing but I mean you have a new state, right? U dagger A prime, which you can call it as a K prime, just for the time being. So this K prime is not, so what you get is, here you get K prime, here you get an operator U dagger ASU. Okay, so this is equal to A prime into K prime. That means this K prime is an eigenstate of the operator U dagger ASU. Okay, or clearly you can say that this what is K prime? K prime is U dagger A prime, right? So if you look at this operator, U dagger A prime is the eigenstate of the operator U dagger ASU. That means AH, right? This is nothing but AH, and with an eigenvalue A prime. That means, how do you represent the base kets? The base kets are represented by the eigenstates, right? So as far as AH is concerned, whose eigenstates are U dagger A prime. So we can say that as time evolves, the base kets changes A prime to U dagger A prime. The base ket changes to U dagger A prime. Okay. So that's the whole point. Alright. Now let's see how the Schrodinger equation changes. Okay, this is for the base ket. This is the so we are seeing in Schrodinger picture as well as in Heisenberg picture. Schrodinger picture, the base kets they won't change, whereas in the Schrodinger picture, the base kets evolves like this under time evolution. Now let's try to see what happens. So let's take derivative of this equation. So we will get d by dt of A prime t, d prime t, which is equal to U dagger. What is U dagger? U is basically e raised to minus I by h cut ht, right? So this is independent of time. So when you have to take du bar by dt, right? So u bar is nothing but so du by dt is equal to minus I by h cut h into u itself, right? Okay. So what will you get? You will get du dagger by dt. Du dagger by dt, which is equal to this minus I h cut, will become I by h cut, right? It will become I by h cut, and then hu whole dagger, you will get u dagger. You get h u dagger, because they do commute each other, so you don't have to bother about it. U dagger into A prime. But this guy, okay. So this is nothing but is equal to du dagger by dt into A prime, right? So instead of du dagger by dt, you can substitute this object, right? So this is equal to, that means d by dt of A prime t, which is equal to I by h cut h u dagger A prime is A prime t. Okay, or you can cross multiply it, it will become minus, okay, so yeah, I h cut d by dt of A prime t, which is equal to minus h A prime. So this is like a Schrodinger equation, but then there is a sign change. So the state vectors obey the usual your Schrodinger equation, but the base vectors, in their Schrodinger equation, there is a change in sign over there. There's a change in sign there. Okay, so now let's try to do this. Okay, let's take this operator AH, the Heisenberg operator AH, and now let's do the spectral expansion for AH. That means given how do you construct by spectral expansion, how do you construct the operator from its eigenstates and eigenvalues? and that's given by, I mean, AH has, the eigenstates of AH is A prime T, right? With eigenvalue A prime. So summation over A prime T, A prime T. A prime T. This is the spectral expansion for AH. Now, I mean, it's easy to see that summation over A prime. And what is A prime T? It's going to be U dagger A prime. And this object is A prime U because it's a bracket, but this is a bra state. So, I mean, this is like this. And now you can take, let the U dagger be there, and then if you sum it over A prime into U, and this, you know that, I mean, this is basically your AS, right? U dagger AS U. So that's AS. I mean, so this is completely consistent. Okay, so yeah. So AH is U dagger, as we already mentioned. AH is nothing but U dagger AS U. Okay. All right. So now let's look at another aspect. I think it's there. Okay. Now suppose that suppose you prepare the state of the system in an eigenstate A prime of the observable A. Now after a time T, you ask what is the probability amplitude that the system is in the eigenstate V prime of the observable B. Okay. If you ask this question, so that means you prepare the system in the eigenstate of an observable A, and you are after time t you ask what is the probability that the system is in the eigenstate B prime of the observable B. Okay. So I mean A and B can be same, but I mean in general they are not the same. Okay, that's what I say. And now in the Schrodinger picture, and so you are asking for the transition amplitude. So you said okay. Okay, just leave that. So what you do? I mean, so the initial system is in the A prime. So Schrodinger picture, the A prime, I mean, like the state of the system will change like U A prime, right? The state of the system is going to change like U A prime, and you are asking, I mean, so what is the probability amplitude that the system is in the B prime state? Okay, because B prime, which is a base state, so it won't, I mean, in the Schrodinger picture, it won't change. B prime, it will remain the same all the time. So B prime, but this is, I mean, U A prime. This is basically the state, right? So it's U A prime. That is because it's a state. It evolves under evolution, under the time evolution. Okay. So this is basically the transition amplitude, and which is called this is the probability amplitude, and it's also called the transition amplitude. It's also called transition amplitude. Okay, and this is in the Schrodinger picture. And if you look at the Heisenberg picture, you know that base states changes, right? So, but the state won't change. It will remain as A prime itself. but the base, it will be B prime T, right? B prime T A prime, and that is nothing but B prime U A prime, because B prime T is nothing but bra B prime into U, because you already said, I mean, how the base case in the Heisenberg picture, the base case A prime, which goes like, or A prime T, which is equal to U dagger A prime, right? So B prime T will be equal to B prime, bra B prime U. Okay, so you can see that the transition amplitude remains the same, whether you take the Heisenberg picture or the, I mean, Schrodinger picture or the Heisenberg picture. I mean, this is basically the Heisenberg. Both are same. Both the steps are the same. I mean, so the transition amplitude in both the pictures are the same.